Let's continue again with Nikola. This time on predicting corpus example quality via supervised machine learning.
Thank you, Simon. So this is joint work with one of my BA students, Mario Peronja, who did the annotation and the analysis of the annotation as part of his bachelor thesis. And first I want to outline the problem. We all know that we need good examples. We want them everywhere, but not only in dictionaries, but in any lexical resource. So many of them being built in NLP. I actually started working on this once I produced a collocation dictionary of Slovene, Croatian, and Serbian, and realizing that since those word forms were normalized, sometimes I would have a problem with grasping what this collocation actually means, and then I needed an automatic way of gathering good examples completely automatically because I don't have the manpower to clean that. But of course, in case of more thorough lexicography, knowing which examples are probably good is also very welcome. So yeah, looking through random concordances is just not the way to go, as we know. So we rank them by the automatically estimated quality of the example. And this is exactly what GoodX does, as you all know. But its flaw, in my opinion, is that it's based on human-crafted criteria. So there has to be a human who understands the problem very well and who's very keen on playing with the problem, and then he shifts those parameters by hand and looks for the results, tweaks them, and hopes to get a good result. On the other hand, if you are happy with the default English GoodX configuration in Sketch Engine, then you don't have this problem. But as long as you have to tweak it, I think there's a simpler way, and this is the one I'm proposing here, but it's not only me, others were proposing it as well at this conference. It's all because of your working group 3, I think. Okay, so we propose an approach where no criteria have to be set by hand, but just good examples and the bad examples have to be chosen by hand, which is anyway something you are doing through your lexicographic work. And then we train a predictor, so yeah, we train a model that is capable for any new sentence to predict how good or bad this example is. And then we rank those example candidates so that at least the lexicographer will be shown only the n best ranked, highest ranked candidates, or in case of NLP, the n highest ranked examples will be included in the lexical resource. So in more detail, how the procedure looks like. So first, we manually annotate a sample of examples for a given headword or collocation, as I will explain later, with its corresponding quality. Next, what has to be done if someone wants to do supervised machine learning is you have to define features you consider informative for predicting the quality of a corpus example. We will talk about them a little bit later. So once you have the annotated data and you have the features, you can train the predictor. This first step is actually the simplest one because there are tools out there that do it for you, absolutely. And yes, we're talking more in the statistical sense. You use features as explanatory variables, so variables that explain the phenomenon, and the manually assigned quality is your response variable. So you model actually the dependence of the response variable to the explanatory variables, and in the future, by knowing the explanatory variables, you can predict or produce the response variable. So this is what you then do in stage 4. So you use that predictor to rank corpus examples of examples that haven't been seen before. So for any potential examples for your new headwords or collocations. So the data set we use are corpus examples from the Croatian web corpus called HRVAC. So so it's not that simple to pronounce. And we were trying to build a real-world scenario sample by taking sentences containing any of the 16 collocations we consider to be our sample. Furthermore, those 16 collocations had actual heads, always heads of 4 mid-frequency lexemes, each being per part of speech. By that, we tried to build a sample which would be both representative for the problem of extracting good dictionary examples for collocations and for head words. Altogether, we annotated almost 1,100 sentences, and each of these collocations were represented with 14 to 99 examples. And we had a 4-level schema we used for annotation, ranging from very bad to very good. You can see the distribution of our annotations down here. So since this is a web corpus, as one would expect, there are more bad examples than good examples. And yes, the two middle categories do have more instances than the two ones in the limits of very good and very bad. And it's almost normally distributed, if we can talk about it, in case of 4 levels. So going over to features, so as I said, once you have the data set annotated, so you have the data the predictor can learn from, you need the features, so the variables by which you define the problem or the information you want to give to your statistical model. So we had 3 types of features. The first type were string-based features. There are quite a lot. I'll just give you a few examples. So the obvious one is the length of the sentence, the average length of a token, the percentage of tokens being purely alphanumeric, whether a sentence starts with an uppercase, whether it ends with a punctuation, the percentage of lowercase tokens, of uppercase tokens, the relative position of the start of the collocation, etc. So those are the features that have been extracted from the text being considered a simple string, nothing more than that. The second type of features we have defined are corpus-based features. So here we start introducing knowledge from some other source, and this is actually the same corpus as we took our examples from, so the Croatian web corpus. And we have 3 features here that are all very similar. So our assumption would be that, as it is with GoodX, I think, if you have very frequent words in your example, then your example should be considered better. So we compiled 3 lists. The first one containing the 1,000 most frequent tokens, the second one 10,000, and the third one 100,000 most frequent tokens. And finally, the third type of features were linguistic features that were calculated from the 2 annotation layers that were present in the HR of our corpus. These are actually 3 layers. It depends on how you count. These are the morphosyntactic layer and the dependency syntax layer. So the corpus were morphosyntactically tagged and dependency parsed. So those features are the percentage of pronouns tokens, the percentage of proper noun tokens. You assume that you don't want these two, at least this is what the theory says. Percentage of numeral tokens, or percentage of subordinating, coordinating conjunctions, number of conjunctions in general, and the last one is the syntactic complexity of the sentence, which was calculated as the average length of the dependency arcs. So we just calculated the length of each dependency arc, and then we calculated the average. So the simpler the sentence is, the lower this value should be. So these are features, and before starting doing machine learning, we did the first introspection of all those features by doing the univariate analysis, which means that we didn't look how those all variables relate. We just looked how good each of these variables or features is as a predictor for this problem. So we report here the p-value, which is actually the probability that the difference between the good and the bad examples regarding this variable was seen by chance. So we want the p-value to be as low as possible. And if it's over 0.05, then it's a consensus more or less, then you can be really afraid that maybe this was really, the difference in these two distributions was happening by chance. As you can see, regarding the string-based features, the most prominent one is actually whether the sentence ends with a punctuation. So this was a deal breaker. So if it ended with a punctuation, obviously it was considered much more frequently a good example or not. We have to take into account, so this data comes from the web. It was clean, but there is always some noise persistent. And the second one was the length of the sentence. So obviously this should be looked into, but probably medium-sized sentences are the ones that people prefer, or at least my annotator, my student, prefers most. All the remaining features are so with a very low p-value, so the probability that the difference occurred by chance is very, very low, except two features. The first one being the percentage of words which are longer than 10 characters. So this is one of the string features. People were claiming that if you have longer words, this should not be a good example, but in our case at least, in those 1,100 examples, it showed to be rather sketchy. So the probability of the difference occurring by chance is 11%, far too much. And the other one being percentage of tokens that are title cased. So title case tokens did not matter. We can look at right away at the proper noun p-value, which was much lower. So proper nouns do matter, but the amount of title casing obviously does not. So going to the second type of features, corpus-based features, here you see a nice trend. So the most frequent tokens you take, the lower the p-value is. So taking just 1,000 most frequent tokens for calculating that features is not a good thing because you are above the 0.05 magic limit. And going with longer lists helps a lot, so the last one is really, really low. Of course, Croatian is a highly inflective language, so here the numbers are probably even, the number of tokens that have to be included is bigger than, for instance, in English or many other languages. And regarding linguistic features, this is quite boring maybe. So the percentage of pronouns showed to be overall the most uninformative feature. Not sure what to think about that, but this is what the numbers say. So the probability of this difference occurring by chance is 40%, which is huge. And the best features are actually syntactic complexity and the number of conjunctions. Here one has, since this is a univariate analysis, one has to think about it for a moment and realize that all this probably correlate very, very highly with the length of the sentence. So this is probably the same information. The longer the sentence, the less good it is, for an example, because people won't be able to read through all of it. And syntactic complexity probably also increases as the length of the sentence increases and the number of conjunctions increases as well. We did some experiments with that, and not all the information comes from this variable, so it does make sense to include these as well. But I will show this a little bit later. So regarding our experimental setup, so we had three actually tasks. First, to optimize our regressor. So similar to Ted Briscoe, here we don't want to classify, but we want to rank. So one way to go is with regression. We didn't do pairwise ranking, but just point-wise ranking. But I think this is almost good enough. We used the random forest regressor. You can use SVMs as well. The results are actually very, very similar regardless of both. We did some hyperparameter search optimization, and we used mean absolute error as the scoring function. This is just for the technical, is more savvy. Second thing we did in our experiments, we used the regressor for ranking. So since we had 16 collocates, we didn't want to train and test on the same collocate. So we divided our data set into 6 actually 16 folds, and we always trained on 15 folds and evaluated on the 16th one. So we still did have the same head word in training and testing data, but at least not the same collocates. And the scoring function, which we should understand, is precision at n. So we calculate the percentage of n highest ranked examples that are, whether they are good or not. So we, for instance, look at the first 3 examples and calculate the percentage of those first 3 that were really good. And we compare with a baseline and a ceiling. And in the third experiment, we remove features relying on external knowledge sources. So this was the corpus frequency information and the corpus annotation. So these two are not, they're not so expensive, but still they aren't given by automatically, so one has to compute them. So to come to the results, so our baseline is actually random order. If you remember the distribution from the beginning, so it's more or less 50%. So you'll have 50% of good examples, 50% of bad examples, regardless of whether you take 10, 5, or 3 top-ranked examples. The ceiling, on the other side, is actually when you use the annotator's choice to rank or to sort, so it's almost 100%. You can see that we don't have always 10 good examples for all the collocates. And we have here 2 settings, regressor 4 and regressor 2. So in the first case, we use all the 4 classes, so from very bad to very good. And the second setting, we only use information about example being good or bad, just to see how much better our predictions are if we use the 4-class schema and not just the 2-class schema. And as you can see, the loss is actually quite low. On the other side, so this could show that actually it doesn't pay to discriminate while annotating the data between very bad, bad, good, and very good, but just it should be enough to discriminate or to annotate only good and bad. But on the other side, this evaluation function doesn't take into account whether the top ones were very good or just good. So it's not that obvious, but obviously there is a loss in information. As you can see, the numbers are always a little bit lower, but not that lower. And yeah, if we take into account only the first 3 candidates, we get in 90% of cases good examples. And if you take into account 10, then it's around 80%, a little bit below 80%. So exactly to discriminate between good and very good and the results, we did these plots. So the first histogram, if you can call it like that, is our baseline. So this is just random sorting. And yes, there are more bad than good examples, as we could already see before. And if you take into account the first 10 examples, then of course there are much, so here we do machine learning and use the results. We have much more good and very good examples than before that. And as you shift towards the top of the ranked list, your results improve. So this actually shows that the algorithm managed to put the very good, so the best examples on the top, which is, again, a good thing. So in the end, we have the same amount of very good and good examples on the top 3 candidates. Once we start removing the features relying on external knowledge, just to see whether this pays off or not in this case. So we have 2 cases, the regressor string case where we remove both of these resources. So the annotation of the corpus and the frequency information from the corpus, meaning the top n tokens, most frequent tokens. And the second regressor lang int being where we remove just one additional feature, which is the percentage of the acritics, since among all the string features, this is the only more or less language-specific feature. And you can see that by removing these outer knowledge sources, we do lose around 2% in case of first 10 candidates, and yes, around a little bit below 4% in case of the first 3 candidates. And if we remove the only language-specific feature, we are still quite good, so the loss is minimal. So if we remove all the feature which is dependent on the language and on external real language resources, we are still okay with 85% precision at the first 3 candidates and 78 on the first 10. So to come to my conclusion, I hope I'm not too fast. So we have presented an approach to extracting good corpus examples by using supervised machine learning, So I think you all know supervised learning, yes, needs annotated data, unsupervised doesn't. Here we did annotated data first and then it learned from our annotation. So the precision on our first 10 candidates was around 80% and on 3 candidates around 90%. As you can remember, the baseline was around 50%. So we do much, much better than just giving concordances in a random order. On the other side, we have to be honest. The most informative features, or even most of the features we use, are very shallow. We actually deal just with how the text looks like and not what the text actually encodes, what meaning it encodes. So we use sentence length and punctuation use mostly. So we have to be absolutely honest here and say that this predictor cannot deal with semantics of a good example in almost no, or to be honest, probably no way. But on the other side, this is where the state of the art is. GoodX does roughly the same, so it just successfully removes the obviously bad examples, so the examples that look obviously bad. And I think the big problem here that could be attacked, and that was partially attacked by, I think, Alexander, by trying to discriminate between different senses, is to move from this level. And still we argue that this approach is much more natural for people than the rule-based approach, where people have to write rules or manually tweak parameters. So here you just really tell the computer, okay, this is good, this is bad, and it learns from that. And you don't have to say, okay, I want only examples that have 62.5 of something, which is much more abstract. And finally, my message would be, that's probably many have already said, so there are some boring tasks in lexicography, as in all the other fields, and machine learning can deal with these tasks very well, so we should leave them to computers and focus on the more hard examples, and there are many of them, as we know. So, thank you.
Thanks.
Yeah, thanks. That was really interesting. You said that your best linguistic feature was conjunctions, and your worst was pronouns. I wonder if you thought about distinguishing demonstrative pronouns from personal pronouns, because personal pronouns are always understandable as, in English, I guess it's the same in Croatian. He, she, not a problem. Yeah. This, that, at the start of a sentence. This is an interesting result. What's an interesting result? You know? So, two different types of pronouns could be very relevant for the quality of the example.
Yes, this is actually a good idea. Yeah, and we haven't done it, and we should take this into account, or at least just measure on this sample whether we get lower p-values if we discriminate between specific pronouns. Thanks.
Thank you. So you were working on, I guess, standard Croatian language, right?
Yes, so
because I would like to see the link to your first talk, where you might also want to describe deviant or whatever non-standard, and then how you would do this kind of job. I guess you could not do it in a supervised manner, but I don't know.
So taking good or finding good examples in non-standard language, this will be the problem. Oh well, so we did actually what I mentioned in my previous talk. We did something similar to that. So good examples of non-standard language would probably be as non-standard utterances as possible, I assume. I don't know. So what we did recently and what we already implemented in the corpus, we built, again, a regression model. So supervised learning, we had an annotation marathon where people annotated good and bad, actually standard and non-standard text among all those different CMC sources. And yes, we managed quite well to predict whether a text is standard or not. Because, for instance, on Twitter, one would assume that Twitter is very non-standard, and we saw that it's roughly as non-standard as spoken language, but still the majority of Twitter messages are absolutely standard and rather not interesting if you are interested in non-standard language. So this could be similar as somehow similar approach. But then the features are quite different, and linguistic features work the best, and these are mostly OOV ratios from various lexical resources, or OOV ratios with allowing some discrepancy, like dropping vowels and similar.
Any more?
Just a short one. Have you looked into correlation between features? Because I have such a feeling that there might be some strong correlation between some of them.
Absolutely. So what I didn't look into all of them, but yes, what I mentioned, that sentence length and most of the the second part of the bunch of the linguistic features, they were highly correlated. So, but I didn't look into the rest.
May I ask about the implementation? What is the output of the software you do? Will it generate, say, the definition for GoodX, or does it work as a separate package, or is it integrated into a?
No. So this is just a scientific prototype, more or less. And yes, it just outputs value between 1 and 4 for an input sentence at this point, if one wants to use it. And I already have used it for this collocation lexicon I built from parsed corpora.
So don't you intend to make it as a module to NowSketch engine?
Maybe. So we were talking about many things that would be nice, but let's see where the projects will lead us and the funding.
Any more? No? Then thank you, Nikola.
Thank you.
Again.
Thanks.